All right, we're going on to section 7.2 today, and 7.2 is about areas in the plane. It's very similar to a type of problem that we did a couple of chapters ago, where we talked about area bounded by a curve and the x-axis. Remember, we used integrals to calculate that, but we had to make sure that we removed any negativity from the function. So if we want to find the area, we could do the integral from a to b of the absolute value of the function. Or we could find the zeros in the interval and subdivide our function into different intervals to find the total area. Because when we're talking about actual area, negative area is not a thing. It is just a concept when we are applying integrals. So here's your warm-up if you want to use it. Maybe looking at number 1, we should be doing it without a calculator. Number 2, we should be doing it with a calculator using that second trace to find the points of intersection. Maybe pause and then come back to the video. So I'll show you the answers right there. Yeah. Moving forward a little bit. Again, section 7.2 is called areas in the plane, and it is a pretty much direct application of integrals. So here, this is a classical problem of what we mean by areas in the plane. We want to find the area of this shape, and I refer to that shape as just like an upside down Nike swoosh sign. So one way that we could find the area between these two curves, we could split this area up into many different areas and add those areas together. So like thinking about this guy as a separate region from this guy, as a separate region from this guy. But that gets really complicated because we have to remember all we know is how to find the area bounded by the x-axis. So we would actually have to split this up into, it looks like 5 different areas and make this really complicated expression down here at the bottom. Let me put that up on the screen so you can see it a little bit better. Now keep in mind, each a that we have there is going to be a different integral. So we'd actually have to calculate 1, 2, 3, 4, 5, 6, 7 different integrals, which is just like really not something I'm about to want to do, right? So instead, we can go through this process. So the process that we go through is we start by drawing some rectangles inside the enclosed region. When I'm talking about drawing the rectangles, we should be thinking about the rams that we did a couple of chapters ago. We should be drawing rectangles with, it doesn't matter where the rectangles meet up. They can meet up on the left, they can meet up on the right, they can meet up somewhere in the middle. Because ideally, we know that we're gonna take this and make our rectangles infinitely skinny so that we can have infinite rectangles up here. And when we have infinite rectangles up here, it doesn't matter where they're gonna be intersecting the curve because that's all gonna be at the same spot. So looking here, here's how I'm drawing my rectangles. Should I zoom in to my screen so you guys can see that a little bit better? Here, see, just drawing these rectangles. And it doesn't matter, the rectangles don't have to be a constant width here because again, ideally, we would have rectangles that are infinitely skinny. By the magic of editing, boom, I got all my rectangles up here, right? So I've drawn all my rectangles. Next thing that I want to do, I want to take an exemplar of one of those rectangles and figure out what the height of that rectangle is. Now the height of the rectangle, I'm talking about this vertical distance right here. And that vertical distance, we can actually see is very strictly related to the curves. This height over here is going to be different from this height over here. So we know we're talking about a variable expression. We know that our height is just going to be the distance in between those two curves. And the way that we find the distance between two curves, let me see if I can have enough space to write this. There we go. Yeah, we're gonna have enough space. The height of my rectangle is going to be distance between here and here is going to be the dominant function minus the non-dominant function. Dominant just means has the bigger value, so it's the function that is upper or righter, depending on which direction you're talking about. So up and right indicate dominance, all right? So that could also be written, we happen to have expressions up here, 2 minus x squared minus negative x. So all of those expressions indicate the height of our rectangles. Let's zoom in here so you can see my handwriting. I know my handwriting is perfectly legible, so zooming in can be helpful. Next, we want to find out the width of the rectangle. And I don't know if you guys realize where we're going with the height and the width. Maybe you will, because eventually we're trying to figure out what is the area of this region. So here we know the width of one of these rectangles is just how far we shoot over for each rectangle. Remember, we determined how wide we made our rectangles. It didn't have to be a constant width, but we know that when we talked about our rams, we talked about our widths of our rectangles being the change in x. Let me zoom this up here a little bit. So the change in x, we'll call the width our delta x. Now delta x isn't going to be able to relate back to the function because again the functions are determined by heights. There. So just zooming in a little bit here. Now I bet you can't figure out what we're going to ask next. What is the area of one of the rectangles? The area of one of the rectangles, and we know that the area of a rectangle is equal to the height times the width. So we can write that in terms of this, y1 minus y2, thinking the dominant function minus the non-dominant function times delta x. Or we can think of it as, in this particular setup, 2 minus x squared plus x times delta x. So whether we're thinking of it as the dominant function minus the non-dominant function, or if we're thinking of it in the tangible example that we have right up here. Now, in order to find the total area, we need to add all of the areas of the rectangles here. So here, we would say the area of the total region, area total, is going to be, this one will be approximately, because again, we have some of those hangy over bits, some of those hangy under bits here. So the total would be the summation of all the individual areas. So the summation of the dominant function minus the non-dominant function times delta x, or the summation of 2 minus x squared plus x delta x, depending on whether we want to talk in general or we want to talk about this specific situation. Now we know, I've been saying it this entire example, we know to find the exact area, we want to make the rectangles negligibly wide. When we make the rectangles negligibly wide, that means we're trying to do an infinite sum because we have infinite rectangles. And we know that infinite sums talk about integration. So here, to find the exact area, the area, and I'm going to put this over here because we're going to need some space to write this out. The area is going to be equal to the integral, again, when I change from the finite amounts to the infinitesimal amounts, the sigma changes into an integral symbol. And we're going to have the integral of, in general, we would talk about y1 minus y2, dominant minus non-dominant, and the delta becomes d. Now, in general, we would want to be stretching from A to B. Now, stretching from A to B, that's just from this point to this point. So those 2 points there, we can actually find those either by graphing 2 minus x squared and negative x and using the intersect feature on our calculator, or we could just do some scratch work and say 2 minus x squared is equal to negative x. Solving that, get 0 on one side, so I'd have 0 is equal to x squared minus x minus 2. Because of how this problem works out, I can factor this where I get 0 is equal to x plus 1 times x minus 2, which gives me 2 equations that I have, either x plus 1 equals 0 or x minus 2 equals 0. Looking at that, I know either x equals negative 1 or x equals 2. Why did I want to put it in that terms, or in those terms? Because now, when I put this in this exact, in reference to this exact problem, I can say that this is equal to the integral from lower to upper of the height here. 2 minus x squared plus x dx. And now there's two ways that I can do this. I could cheat and I could grab my calculator and I could type it in, but that's not fun. The fun way to do this is take the antiderivative, so we get 2x minus x cubed over 3 plus x squared over 2, run it from -1 to 2. Am I going to have enough room to write it in here? I think I will. That would be 2 times 2 minus 2 cubed over 3 plus 2 squared over 2 minus, evaluate at the lower, so lower is -1, so 2 times -1 minus -1 cubed over 3 plus -1 squared over 2. Yeah. Okay, so now that's scary, especially since I have some fractions dealing here, so I'm going to start simplifying it. I think last time I checked, 2 times 2 is 4. 2 cubed is 8, so 8/3, plus 2 squared over 2 would be 4 over 2, or just 2. That's this expression right here, minus, let's put that in parentheses to keep it together, minus quantity -2 minus -1 cubed becomes negative, so this should be plus 1/3. -1 squared would be positive 1/2. So carrying this out a little bit further, I could probably distribute my negative. I'm going to get, okay, this is hard. 4 minus 8/3 plus 2 minus 1/3. Again, I'm distributing my negative throughout here, so minus 1/2. So now I can see I've got 4 plus 2 plus 2, 8, negative 8/3 minus 1/3, 9/3, so minus 3 minus 1. Okay, almost there. Wait, not minus 1. The heck is wrong with me? Not minus 1. There we go. Minus 1/2. This guy right here. All right, so 8 minus 3 gives me 5. 10 halves minus 1/2 gives me 9 halves. Final answer of 9 halves. Yeah. It just feels so satisfying to be able to do that by hand and then possibly pull up your calculator and see if you're right. I don't know. I'm going to keep my fingers crossed. Yeah, look at that. So again, I really don't care how you do it, whether you do it by hand or you do it by calculator. It makes me feel better to do it by hand just because it's just, look at that. Isn't that just impressive? But again, in this chapter, I'm not testing you on how to calculate an integral. I'm testing you on what the area is. So looking up here, we've now established how to find the area between two curves. If f and g are continuous with f greater than g, meaning f is the dominant function throughout the interval from a to b, then the area between the curves y equals f of x and y equals g of x from a to b is the integral of f minus g from a to b, meaning we can jump right to when we want to find the area between two curves, the area is equal to integral from a to b of f of x minus g of x dx, as long as f of x is the dominant function. Okay, there is a cheat to this one if you want to see it. If you are going to use a calculator, which sometimes does pop up, you can remove any negativity from the function really easily. The cheat way to do this, if you grab your calculator, is the area is equal to the integral from a to b of the absolute value of f of x minus g of x dx. Just like a couple chapters ago, if we put the absolute value around the integrand, we remove negativity from that height. Remember what happens if we do the non-dominant minus the dominant number? You're just going to get a negative. It'll be the opposite of what we're looking for. So just taking the absolute value of that is going to work. Again, that's only if you have your calculator at your disposal. I'm going to try to do these without calculators. Like looking here, we want to find the area of the region between y equals cosine of x and y equals sine of x. First off, we want to make sure that on this interval, we do not switch dominance. If we do switch dominance, we need to subdivide our interval into the regions where the dominance switches. So we want to find out where the two functions intersect here. But I happen to know that the graph of cosine of x and the graph of sine of x happen to meet up at pi over 4. That's where we intersect those two functions. At pi over 4, both of these values are at pi over 4, comma, root 2 over 2. Again, could I just graph that and look at it? Yeah, absolutely. If I wanted to graph it, I could, let's pull up my calculator. And if I go into my y equals menu, I could graph y equals cosine of x. I could graph y equals sine of x. I could make sure that I only go over the indicated interval. So I'm going from 0 to pi over 4. I know that cosine and sine really don't go that high. Goes down to -1 and up to 1. So looking at that, I can see, yeah, no switching of dominance because the blue is above for the entire interval. Now, the blue there happens to be the cosine function. So we know in order to find the area, we have to do the integral from the beginning to the end of the interval. So the beginning of the interval, oh, hey, they give it to us. 0 to the end of the interval, pi over 4. And then we want to do dominant minus non-dominant function. So again, the dominant function here is going to be the cosine of x minus the non-dominant function, sine of x dx. Again, if you're using a calculator, it doesn't matter. You don't have to identify dominance and non-dominance. You just do the absolute value of one minus the other. But again, I'm trying to do this without my calculator. So here I know that I want to put in my parentheses the antiderivative of cosine, which we know after struggling so much last chapter that is positive sine, minus the antiderivative of sine, and we know after struggling so much last chapter that is plus cosine of x, and we're stretching from 0 to pi over 4. So again, we know that we're going to be talking about the sine of pi over 4 minus plus cosine of pi over 4 minus sine of 0 plus cosine of 0. I happen to know from my unit circle, if I look at it, pi over 4 right up here, that's the symmetric one, root 2 over 2, comma, root 2 over 2. So sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2 minus 0 is down here at 1 comma 0. So sine of 0 is 0 plus cosine of 0 is 1. So now we've got root 2 over 2 plus root 2 over 2 ends up being root 2 minus 0 plus 1 minus 1. So our area is equal to exactly root 2 minus 1. I would want to leave it there because that is an exact answer. However, just to show that we are fun people, we could go to our home screen and we could have, fn int from 0 to pi over 4 of, I don't feel like typing those functions in here. So I again remember y1 is my dominant function. I'm going to cheat on this. y1 minus y2 dx. Yeah. Approximately 0.414. I don't care whether you give me the answer of approximately 0.414 or if you give me the answer as square root of 2 minus 1. They're the same thing. It's just I happen to be cooler the way that I did it. If you don't want to grow up and be cool, that's fine. That's fine. You can do however you want to do this. Oh, something that I forgot to do. I forgot to draw my boxes in here. So I'll try to remember to do that every single time tomorrow. I'll try to draw in the shading to see the region. Maybe, here we go. Find the area of the region enclosed by the parabola y equals x squared minus 1 and y equals x plus 1. So the first thing that I would do, I would sketch a graph of this. You might need your calculator for this one. I don't know your life. I happen to know that this looks like that, the x squared minus 1, and the x plus 1 looks roughly like this. I know that I'm going to be coloring this in. I want to shade in this. It looks like, again, that upside down Nike swoosh. I know since everything is in terms of x, I want to use what we're calling vertical strips. So when I color this in, I want to draw in using just vertical lines. And what this really does is this allows me to remember that I'm actually drawing in those rectangles to try to find the area. And it also gives a nice look to that shape, right? So now I can see the dominant function is the linear. The non-dominant function is that x squared minus 1. I need to find where they intersect because I don't have my limits. I'm trying to find out what this is and what this is. In order to find those out, you could use your calculator and graph them, but that just feels so gross to me. I like doing it this way. Doing the x squared minus 1 is equal to x plus 1. And getting 0 on one side, we'd have x squared minus x minus 2 is equal to 0. Factoring that, x minus 2? Yeah, x minus 2 times x plus 1. It does not factor as the same as that original problem, does it? So now we can see x minus 2 equals 0, or x plus 1 equals 0. Oh, that stinks. X equals 2, or x equals negative 1. Well, we'll have to make sure we do a problem that's different from this one next time, tomorrow. Now we can say that our area is going to be equal to the integral from the low to the high. Now looking at this, since everything is going to be in terms of x's, we are using our x coordinates for our lower and our upper limit. And again, we're going to stretch from small, pen went bye-bye, negative 1 to big 2. And we want to do dominant minus non-dominant. Again, the dominant is going to be the linear function, that x plus 1, minus the non-dominant, which is the quadratic x squared minus 1. Now, I would point out here something that I kind of shuffled past in that one. You want to make sure they use parentheses around the functions, because when we simplify this before we even integrate it, we would have to distribute that minus, so we'll have x plus 1 minus x squared plus 1 dx. To make this easier on us, we'll stretch from negative 1 to 2 of x plus 2 minus x squared dx. And again, my whole goal is to do this without a calculator. So I'm going to find the antiderivative. Antiderivative of x is x squared over 2. We know that rule from last chapter. Antiderivative of 2 is 2x minus x cubed over 3, stretching from negative 1 to 2. So I know that I'm going to have 2 squared over 2 plus 2 times 2 minus 2 cubed over 3 minus negative 1 squared over 2 plus 2 times negative 1 minus negative 1 cubed over 3. And now just arithmetic. Hopefully I don't screw it up this time. Oh wait, you guys didn't know that I screwed up the last one. I had to record it twice. 2 plus 4 minus 8/3 minus negative, 1/2 plus -2 plus 1/3. So 2 plus 4 minus 8/3 minus 1/2 plus 2 minus 1/3. Is this going to be the exact same value? Dang it. 2, 6, 8 minus 3, 5 minus 1/2. Yeah. 9/2 again. So the area is 9/2 square units. So again, this is what we call the vertical strip method. There is something called the horizontal strip method. I said there is something called the horizontal strip method. The horizontal strip method comes up when you have functions that can't be solved for y. Like x is equal to f of y. You can use this strategy. That pops up sometimes. A lot of times when you have horizontal limits, like in this problem where our one limit was one edge was a vertical piece, we see over here we have a horizontal limit there. So if you have a horizontal limit, using horizontal strips would be easier, because then when we color in, we can just draw like this, and we can color in that way. Notice that now we just have sideways rectangles that we're coloring in there. So it's still going to be the same kind of idea. We still want to do dominant minus non-dominant in our integral, but now we want our lower limit and our upper limit to be in terms of the y instead of in terms of the x. And here, dominant means further to the right, non-dominant means further to the left. Look in here. Oh, here we have some problems. Find the area of the region bounded by the curves x equals y squared minus 1 and y equals x plus 1. First off, I'm seeing up here x equals y squared minus 1. I know that's going to be exactly like a curve of y equals x squared minus 1, except it's going to be sideways. So it's going to look roughly like this. And I know that the graph of x plus 1 is going to look roughly like that or so. I now know that, let's see, I want to find my points of intersection. So my points of intersection, man, I can't set these equal to each other because I've got x equals and I've got y equals. So here I'm going to have to start this by subtracting 1 so that I can get y minus 1 is equal to x. So now I have two functions where x is solved. I can clearly see that I want to draw in horizontal strips there. Now to find my boundaries, I'm going to take y minus 1, set it equal to y squared minus 1. Solve that any way I know how. Let's see. 0 is equal to y squared minus y. Add 1. Oh, plus nothing. Okay, cool. So this becomes 0 is equal to y times the quantity of y minus 1, which means either y equals 0 or y minus 1 equals 0. So my two limits are y equals 0 and y equals 1. Again, I know that I'm talking about functions. I'm talking about my y variables because I have x solved for. X solved for means I'm doing everything in terms of y. In terms of y means use y as my limits. Now I have to figure out which function is dominant. Oh crap, I don't know how to... Oh, here's one way that we could figure out which function is dominant. One, we can look at the graph and I can see that my linear function is further to the right than my quadratic function. The other way that I can do this, I can find x of some number in between 0 and 1. So x of 0.5. So x of 0.5 would be 0.5 squared minus 1, so 0.25 minus 1 gives me negative 0.75. I can also do that over here. X of 0.5 is going to equal 0.5 minus 1, which is going to equal negative 0.5. Which of these two numbers is bigger? The bigger number is the dominant number. Since we only switch dominants at 0 and 1, the dominant function is going to be the one that yields that negative 0.5, which is this x equals y minus 1. That's going to allow me to say my area is equal to integral from lower to upper, 0 to 1 of my dominant function being y minus 1, minus my non-dominant function, y squared minus 1, dx. And now evaluate however you want. By the way, if you didn't want to get into the weeds as far as which function is the dominant function, just do the absolute value of one of the functions minus the other function. It gets you the same place. So here we'd have integral from 0 to 1 of y minus 1 minus y squared plus 1 that was supposed to be dy. Equal to integral from 0 to 1 of, that'd be that easy, y minus y squared dy. And now I'm going to integrate. I would have antiderivative of y is y squared over 2 minus y cubed over 3, stretching from 0 to 1. So we've got 1 squared over 2 minus 1 cubed over 3 minus 0 squared over 2 minus 0 cubed over 3. That's gone. All we're left with is 1/2 minus 1/3. And here's where I always suck. Common denominator 6. 3/6 minus 2/6 equals 1/6. We have an area of 1/6 in that little almond slice right there. Sweet. I think that was the last problem that we wanted to do. Pretty sure. Yeah. General strategy, sketch the curves, decide on vertical or horizontal strips, pick ever which one's easier to write the formulas for, or whichever one lets you integrate fewer times, looking at the orientation of the boundaries, whether you have vertical or horizontal boundaries. Write an expression for the area of the strip. If the width is dx, the length must be in terms of dx. If the width is dy, the length must be in terms of y. 4, find the limits of integration. If using dx, the limits are the x values. If using dy, limits are the y values. And integrate to find the area. End of story. We'll practice tomorrow. We'll go through some of these problems. This is fun stuff. I really like these applications. And I will see you guys tomorrow.